Hi everyone, it's Jimmy here. So welcome to the fourth episode of my analytical mechanics. It's been a long time since I updated my video because previously I've been preparing for my some contests. Just last week, I have finished my physics ball contest. And before I finished my SAT examination. Anyway, I'm finishing up all my exams, and now I have time to update my video. In this episode, it's mostly like a catch up episode. So it concludes as contents from my previous three videos, and it's like a review. But there's something new in here. So in this video, I'm going to talk about how to integrate the equation of motion based on what we have learned so far. Let's review what we have learned. We have learned about Lagrange's equation, which appears in our first episode, I think. Yeah, it's in our first episode. So it takes the form where is it? It takes the form like this. And then we learn about because the conservation laws based on the Lagrange's equation. So energy, momentum, and angular momentum conserves under certain conditions. We must note that. And for further details, you can check my last videos. And in the third episode, we talked about potential energy. So yeah, it's a very important element in analytical mechanics. So in this episode, I'm going to talk about how to use these concepts to integrate the equation of motion. So for a given system, we can first observe how the things in it are placed using, and we put the system in coordinates. Remember what we talked about in the first episode about generalized coordinates? So to sum up, it got rid of here. So it got rid of the restrictions of the XYZ. We don't need to choose these coordinates we don't need to choose it. We can use any set of coordinates that as long as it satisfies as long as you can use it to describe the motion and the time evolution of a system. So back here, so we put this under a set of coordinates and write out its coordinates so that we can describe its positions. And then taking one order derivative, we get x prime, y prime, xy prime, xyz prime. Suppose we use the xyz coordinates. Anyway, you don't have to. So we get x prime, y prime, z prime. So this what we get here is velocity. So and then we can from velocity based on velocity we just derived, we can write out T, which stands for kinetic energy. Kinetic energy. So which is one of the components of the Lagrange's function. And then we can we can work out based on the position of the objects. We can work out the U of the system, which stands for potential energy. So, we talked about the last episode, I think, the potential energy is only depends only on positions. What we put over here depends only on positions. So as long as we have the XYZ of the system, we can write out the U, the potential energy of the system. So now we have already derived the two components of the Lagrange's function, and the Lagrange's function takes the form of T minus U, and then we can write these out, and and then we use the Lagrange's equation back here, and then we can derive the equation of motion. So some of you may notice that I put this episode as the first episode of integrating the equation of motion, because then we are gonna have a second episode which encompass more complex problems, and we need not only this concepts to solve it. We need cyclic coordinates and also effective potential energy. That's another concept, totally different. Anyway, I'm going to talk about it in my next video. So here I gave example. So it's double pendulum. looks like this. So it's like one string with a ball and one string with another ball, but the second string and the first ball is connected, so it swings, but in a more complex motion. It may seem difficult, but under analytical mechanics spheres, it's quite simple, I think. But this calculations may seem complex, but it's really quick if you understand all these concepts and master it. So we take a look at it, and first off, we put it under the xy coordinates. But as I said before, you can put it in any coordinates as long as you can describe its motion. Anyway, for convenience, we use xy coordinates here. So we note here that the right stands for the positive side for the x value, and the pointing downward, it stands for the positive side of the y value, meaning that if we go down further, the y value will increase. So it's a little bit different, but I think you guys can accept it. So let's take a look at the first ball, M1. So it has the mass of M1, and the rope hanging from the pivot is L1. It has the length of L1, and its degree is phi 1. So it will all change, except for L1, and only phi 1 will change as the passage of time, because it's swing. So actually for the first ball, we don't need to work out its coordinates in order to get its velocity, because for a circular motion, we have the formula velocity equals to angular velocity times r. In this case, the r is of course its length L1. So we have already know the radius of the motion, but the angular velocity we can get from taking a first order derivative of the the angle hanging. So we don't have to put it in the coordinates to get the velocity of it. So anyway, its value, and we put it into the formula of kinetic energy, this, and then we get this. This is quite simple until here. And the potential energy, of course, it's only encompass the potential energy of gravity. So we note that we chose the downward side as the positive side for the y-axis, so we must put negative sign before this term. So yeah, from the geometry in the graph, L1 cosine phi 1 equals the length of, if we draw a line perpendicular to this is equals to L1 cosine phi 1, and then that's all for mass 1. And because we already know the kinetic energy and the potential energy of this ball, so we can also work out the Lagrange's function. And then for the second mass, M2, in this case we must put it in the coordinates because of course I think you guys have already noticed the pivot is also the original of our coordinates, because it's convenient. So for the second ball, after we put it in the general the coordinates are here, over here. It's simple geometry, and then after taking the first order derivative, we get this. So these two are the velocity of M2. These two terms are the velocity of the second ball in the x direction and y direction. The little hat means direction. So after working out these two components, because we put it in this coordinates, so its velocity is equals to its velocity in the axis plus its velocity in the y-axis. So we put it back to this first formula, and we get this. Again, it may seem very difficult, but the calculation is quite simple. The logic behind the calculation is simple. And then, similar to what we did for the first ball, we can also work out the potential energy for the second ball. It takes a form like this. So we only have two balls in the system. It's quite simple. So we add them together. It's what we get as the total kinetic energy. So add these two up, and then the potential energy is the same. We add these two up. And then from our steps, we can work out the Lagrange's function for this system. So we divide potential energy from the kinetic energy, and we get this long term. I'll stay here for a second, unless you guys can check my calculations on your own. And then we use the Lagrange's function over here, and Lagrange's function we replace the phi instead of we don't use q, because in Lagrange's function q stands for generalized coordinates, but however in this case we used more of the angle, this angle as a element to describe our motion. So we replace qi with phi, and then we can put all these formulas into this. Put all these formulas into this equation. We just work out the Lagrange function for the system, so we can put this back into here, and then we can work out the equations of motion for these two balls separately, like this. So the calculations, you guys can check this on your own. If there are any mistakes, please type it out in the comment section. So that's all for today. I think it's not very difficult, because it's consists only about Lagrange function and Lagrange's equation. But in our next video, the second episode of integrating the equation of motion, we'll introduce some new concepts and talk about ways to integrate the equation of motion for more complex systems. So that's all for today. Thank you guys for watching.